In this video, I just want to work a few of the types of problems you're going to see here with you so that you know kind of exactly what is expected and what it is you're going to be doing. So let's start with example 1, which you see right here. We're given a set of data and we are asked to write the equation for the curve of best fit. So that is, find the regression model for this. Give me an equation for it. And then we're to find the value of the function when x is 9.4, which you'll notice is not one of my given values, and for when x is 29.3, which you'll notice is way beyond any of the given values that I have there. So what we're going to be doing here is using our equation that we get to make predictions. So the first thing we have to do is actually get the equation itself. And so over here on the right, you can see I have the Desmos tool open. Notice that I don't have the graph. For these questions, you won't need the graph that you get from the Desmos regression at all. You'll just need the data that you get from down here in this screen. So what I'm going to do first is type in all the data. And now that I have all the data typed in, I want to look at what is given to me down here. And so what this will do is this will tell me my equation for the curve of best fit, which will be a quadratic in this case. And so for my problem, I would just come over here and I would say for problem A, my equation for the curve of best fit is going to be y equals negative 1.732, and you can go ahead and round off to the thousandths place on all of these, times x minus 4.793. All of that is squared. Don't forget that. That is easy to forget. And then plus 0.288. That's going to round up. And so there we go. There is my equation for the curve of best fit. All I did was read that off of here. So that y1 I would write down as just a y. The 1 in that is just telling Desmos where to look. Instead of the tilde there, I would write the equal sign. The tilde, that squiggly line, is just to tell Desmos to do a regression. And then instead of x1, I would write just an x. Again, that 1 is just something to tell Desmos what to look for. I got those numbers from right here. There's A, H, and K. So all I have to do is read those off, substitute them into this equation, and boom, I have all my data. Now the other thing I can do is look at my r-squared value and tell whether or not this is a good fit. And the r-squared value for this one is 0.999, so this is an awesome fit. This is as good as you're ever going to find. So huzzah, that's good stuff. Alright, for part B, what we're asked to do is find the value of the function when x equals 9.4. So now I'm going to make a prediction. I'm going to say if this equation is a good fit, and we can see from its r-squared value it's an awesome fit, then what we're going to do is use that equation to find y when x is 9.4. So in order to do that, all I have to do is take my equation, negative 1.732 times, and then instead of x, I just have to substitute in the value that I'm looking for, 9.4 minus 4.793 squared plus 0.288. And once I do that, that's something that I can simply type into a calculator. Be very careful about any parentheses and negative signs and such. But that's something that I can type directly into a calculator and actually just find my solution from that. After crunching some numbers in the calculator, I find that for part B, y would be equal to negative 36.473. Notice again I'm rounding off at the thousandth place. That's what I want you to do for all of these if you're not told otherwise. So negative 36.473. And the other thing I can do is see if this makes sense. If I'm looking for a y value of 9.4, it should be in between these two values, in between 4.9 and 11.3, and it should be much closer to the 11.3, and so we can see negative 36 is in fact between 3 and negative 65, about where we'd expect. So that's good. I can make a prediction from within my data, like in part B, or in part C, what I can do is I can look for information outside my data. 29.3 is way bigger than any x value that I have in there. But just like I did with part B, all I have to do is substitute that into my equation. So I'm going to say now in this case 29.3 minus 4.793 squared plus 0.288. And again, all I have to do is crunch those numbers in a calculator and I will have my prediction. So in this case, the value would be negative 1039.939. And again, I can check and see if this makes sense. These numbers, as x gets bigger, are getting bigger in the negative direction, and so we would expect some number to be much smaller than negative 374, like negative 1000 is. So it passes the smell test. It makes sense. All right, for part D, we're asked to find the vertex of the function, and you might be tempted to go to your Desmos graph to do this, but as it turns out, we don't need it at all. We have that information sitting right up here in our original equation. So if we look back up here, I can see my x transformation and my y transformation from the parent function y equals x squared, and I can read off my coordinates for the vertex right from that. So the negative 4.793 negative inside the parentheses like that means it's going to move to the right 4.793 places. So my x coordinate would be 4.793. Notice that's the opposite of whatever number was in here. So if that's a negative, it's going to be positive down here, and if it's a positive, it'll be negative down here. And then my y coordinate, well, starting from 0, 0, I shifted upward 0.288. So my y coordinate is 0.288, and that's my vertex. Again, I can get it straight from the function. So there we go. There is one example of this. There's just one more thing that I want to show you on with problems like this, and it doesn't even require that we work out the whole problem, but rather I just show you the first step of the setup. So let's take a look at that now. I'm given the same questions, so I'd work them in exactly the same manner as before, except this time I'm given dates instead of my usual x values. Now there's nothing, and I mean nothing, wrong with going ahead and plugging in these numbers as numbers for your x values. The only thing problematic about that is that 2007 is not a small number. So what I typically do when I have situations like this where I'm dealing with years for my x value is to take whatever my first year is, and let's just call it year 0. And so the next year after that, 2008, was 1 year later, so let's call it 1. 2009 was 2 years later, so let's call it 2. And now here's where we have to be careful. 2010 would be 3, so 2011 should be 4. And then 2012 would be 5, so 2013 is 6. And then 2014 would be 7, and 2015 would be 8. So now what I can do is, instead of having these big numbers, which are going to force me into having an equation with big numbers, I can just use these, the 0, 1, 2, 4, 6, 7, and 8, as my x values, and then get my curve of best fit, find all the other problems. You would have to translate through to all of these. For instance, finding the y value in 2010. Well, under this system, 2010 you would not put in as 2010, but rather 3. In 2016, you wouldn't put in as 2016, but rather as 9. It's 9 years after 2007. So that's a substitution that you can make just to make the numbers a little bit easier to deal with. Good luck, guys.